Hello and welcome to another lecture. In this exercise, we're going to go ahead and design a moment connection between a beam and column. There are many different types of a moment connection. The one we're going to use is a shear plate bolted moment connection. Let me show you how many different types it is. If you go onto a SDS2 website right here, they have a really a good website for detailing. And in here you can look at the different type of moment connection. There's a clip angle, there's a clip angle moment, this type. The guy we're going to use is this one right here. It's the shear plate bolted moment connection. We're basically shear going to be created by this plate right here, and the moment's going to be right in the flange, and we're going to design that. You can go through this and find out the different type of moment connection. Okay, let's go over the problem, see what we need to do. Alright, here's the problem. So we're going to design a shear plate bolted moment connection and verify the bolted flange plate fully restrained moment connection between W18 by 50 beam and a W14 by 99 column based on the vertical reaction for dead load is 7 kips. Vertical reaction for live load is 21 kips, and the moment dead load and live load are 42 kip foot and 126 kip foot. We're going to use 70 KSI electrocode welding ASTM grade 50 material. So let me make this picture a little bit bigger. And this is exactly what we're going to do. We're going to have a plate on top and a plate on bottom. But I want to tell you something first. A lot of time you see it in the field, what they do, they bring in the flange itself, they weld the flange to the column, and that's one way they do it, and then you can put a stiffener plate on top of it. In this case, we just have the flange is about inch away from the face of the column, and then we have this top plate welded, and the bottom plate is welded, and then we have the shear plate welded on both sides like this one. Sometimes, let me see if I have that explanation right here. Sometimes you're going to have a situation like this picture. Maybe not. Maybe when you design this plate, maybe the weld, you come up to the length of the weld. If the length of the welds is bigger than the flange itself, then you might have to put additional stiffener on it. And I have put this in writing right here. You can pause the video and read it. And this is where we're going to use how to calculate the length of the weld. And again, hoping that it's less than the flange width. And if it's not, then we have to use the auxiliary plate. And you can look that up and AI it, and you can find out, or you can read it right here. But before I continue to solve this problem, because you're an engineer, you're pretty smart if you're watching this video already, let's go ahead and see if you can solve this riddle. Harvey's wife is 6 years younger than her husband. One day after working on a mathematical formula, he remarked to her, "Did you know, June, that we have been happily married for 22 years? And since our marriage, our combined age have exactly doubled." How old were they when they were married? See if you can figure that out. I will put this answer on my next video. Good luck to you. And I want you to put the answer down the bottom at the comment. All right, let's get to work, solve this problem. Okay, so assuming this is the column, we've got the column right here. I want to do a moment connection. So we got this top plate, which is for the moment, and a shear plate right here. We're going to size both plate. We can size these plate as wide as the flange itself that comes into it, and then both top and bottom based on weld size. And what we can do here is then we can, based on experience, we can do 2 lines of 4 row of bolt, or start out with 4, go to 6 and 8, and then see how calculation works out. But we're going to start out with the 8 bolt right here. So if you have the flange right here going into it, and this will be the beam coming in here. We can basically go ahead and if you kind of like this will lines up with the shear plate, and your top plate should really be about your flange plate should be 1/4 inch smaller on each side of the your beam flange. So if the beam flange is 7.5, you want to make your plate 7 inches. Okay, this is going to be a long problem, so what I'm going to do, I'm going to write this stuff down ahead of time and then explain it, so hopefully we can go a little quicker. So here we have the column right here, and then we got the plate. We want to size these two plate, and then we're going to, once we size the plate, we're going to based on a weld length, and then we're going to put a bolts in there and verify, go through the whole things. So the first thing I did, to go ahead and went to table 1 ASCE down for the column and the beam. I got all the information for D and BF and TF and TW, all that stuff. And then we're going to use LFRD. We're going to use LFRD method. It's quicker this way, but I like ASD too also. So let's just stick with this one. And first I'm going to size the moment plate plus weld. The moment plate will be this plate up here. This is the moment plate on top of the flange, and let's size that one first. And we got, based on the load we had, I'm going to calculate the MU, which is 1.2 times dead load plus 1.2 times live load, and I get 252 kip per foot. And then you saw that in the PowerPoint, and I will bring it back on again in a minute. We calculate the tensional compression, which is basically multiplying, dividing moment by the D minus the TF. You've seen this before. So that will give me 173.5 kips. Once I have that, I'm going to come in here, calculate the area of the groove weld, which is equal this number divided by phi times Fy, and that will give me area of the weld. When we did the welding connection, we did a lot of this, and if you already done this, you know how to get to this anyway. Basically follow any welding example. So now we have that welding area. We're going to find out the weld length. The weld length came out to be basically this area divided by the thickness of the flange, and which is 385 divided by 0.5 is 676. So let's go back. We say going to use 7. If I come back right here, 7.5 right here. So this is 7.5 inch right here, and we're going to go ahead and use a 7-inch plate. And I want to know what is the, how much weld do I, 7-inch weld around this area, and what kind of plate we're going to use. Well, we're going to use a 4-hole, and like the way we have it, and per ASCE, each distance between hole got to be 3 inches standard. So I got 4 times 3 is 9, and you got to be about 2 inches away from the edge, so the construction worker they can get the sponge wrench in there. And from here, per the code, you can be 1.5 inches away from the center of the hole to the edge of the plate. So that will give me about 9 and 2 is 11, 1 is 12, 1.5. So that makes it 12 inch and ½ inch. So let's come back here and size this plate. So let's make this green so it will be okay. That will be I'm going to say this is a 3/4 inch plate thick time 7 inch time 12 inch 0.1/2, and that's the size of the plate. Let's go ahead and size the shear plate. So the shear plate, what I did is here, come back in here, we're going to calculate the RN design for the shear weld. We're going to try 1/4 inch fillet, and for the other one we're going to just use 3/8, and then we're going to go ahead and calculate the RN of weld per inch. That's given by this equation. You've seen this before. Then we're going to go ahead and plug in a number which is 0.6 times 70 KSI electrical times 1/4 inch fillet times 0.707, giving us kip per inch right here. And then we're going to calculate the shear, which is RU is equal to 1.2 times 7, 1.6 times 21 to give us 42 kips. Next thing we're going to calculate is phi times RN, and that would be 0.75 times that. Then we calculate the wall length, which is equal really 42 kip per inch divided by 556. It gives us 7.5 inch. So now we're going to come back in here. We want to know what length is going to be. So if it's 7.5, you want to put 1.5 inches on both sides of the hole. That will be this will be 3 and 3 be 6. 6 plus 3 be 9 inches. So right here will be 9 inch wide, and my plate is going to be if we use 3/8, let's use 3/8, and then we will do a verification, see if it's going to come out correctly. So it's going to be 3/8 by this is a, you can make this plate 5 inch. I wrote it 5 inch, so make it 5 inch by 9 inch. So now come back in here. What I did here, I said, okay, we're going to use a 3/8 weld on the top plate and the bottom, top and bottom, and then we're going to use 1/4 inch weld on the top and bottom for the shear plate, and for the bolt we're going to use 8 bolt right here. That's be 8 bolt right there, and if we use 8 bolt, and that will be 7/8 group 120N, and for this one we're going to use same thing, 3/7/8 120N. And if you don't know what 20N is, let me go to the PowerPoint for a second. Right here we have the concept of the thread included bolt. Sometimes in the shear plane you have the thread included, and sometimes it's excluded like that. And this is a thread included in the shear plane right there. You see it. This plate going this way, plate going that way. And if it's not included, excluded is like that. Normally when it's excluded, the capacity is higher. And there's a lot of good reading right here. You can go ahead and read it yourself. And okay, let's get back to the writing. Okay, so recapping this, the flux work strength of the beam per ASC section F13.1, and then we're going to use the area, net area per section B43A and B43B. We're going to calculate area of the flange. It comes out to 428. The net area of the flange is we're going to have 2 bolt hole, so that's where we're cutting it. And minus plus time DH plus 116. DH from J38 is 1516, and time the thickness of the flange. So now we put all those numbers in. The net area comes out to be 314, and the then we're going to calculate Fy over Fu comes out to be 0.679, which is less than 0.8. And if you look at the section F13 on the second page, it says Yt is equal 1. Then we're going to come in and calculate the Fu AFG, comes out to be 204.204. Then we calculate Yt FYAG, comes out to be 214, which is bigger than 204. So when this happened per section F13, take a look at it when I have it on a board. I'm going to write down therefore basically the nominal flux work strength of MN at the and the tension with the holes are, not bigger than MN. And again, this is, if you read that section F13.1, this is basically what it says. So if you plug in a number, that comes out to be 204 kips divided by 4.28 time 88.9. I think it was 88.9 at the beginning. Let me check. Yeah, right here. So that's time 88.9. That will give us 4,240 kip inch. Let's divide that by 12, and that become 353 kip foot. Basically divided by 12 to get this number, 353. Okay, so now we have that. We can go ahead and phi for bending is equal 0.9, you know that. And phi b MN comes out to be 0.9 times 353. That gives us a 318 kips, which is bigger than the load, which was 252 kip foot. Should be a foot right there. So this is the capacity, and this is the load. And at the beginning we did calculate that the came out to 252, and that was 1.2 times dead load moment plus 1.6 times live weight moment. Okay, we passed this, the fluxual. Okay. Okay, next we're going to go ahead and look at the single plate weld connection, strength of the bolt connection. If we go to AAC section J3.7 and J3.11, actually let me see the PowerPoint. I got a commentary here. Yeah, so it says from AAC specification J3.7 commentary, the strength of the bolt group is taken as the sum of the strength of the individual fastener, which may be taken as lesser the fastener shear strength per AAC J3.7. The bearing strength of the bolt hole J3.11 or tear out group could be by J3.11. So now let's go back to, we're going to go to table 7.1 to figure out what is the strength per bolt is. Let me close this out here, and it comes out to be 24.3. How do I got that? Let me see if I can show it to you. You can see right there, and for a 7/8 diameter is 24.3, right there. Okay, next we're going to go into, let me bring up, this is the 15th edition, but I'm going between 15th and 16th because I got the 15th PDF. I don't have a 16th PDF. So using this equation, this is when deformation of the bolt hole at surface load is design consideration, Rn is equal to 2.4 dt Fu. So let's work with this. Let me close this out. So next we're going to calculate the available tear-out strength of the plate at the interior bolt, which we're going to use the section J3.11a, and that's going to be equation J3-63. So let me see if I can get the camera on this here. Here's the equation right here. Can't see that well. Okay, we're going to continue with that using the equation J 3-6C. This is the J 3-6C. We're going to calculate Rn, and then we're going to calculate phi times Rn, comes out 45.2. So now we have this one, and this was for the group tear out, and then we had this one. What was it? There's this one here also. And this one. Controls. The lowest one controls was 24.3. Okay. Okay, so now, so we found out the bolt shear controlled over the bearing and tear out at the interior edge. Now we're going to look at the edge bolt. And to the edge bolt, let's find LC. LC, if you look at the same page that I told you, you can find a definition for all those. And LC is basically the clear distance in the direction of the force between the edge of the bolt hole and the edge of the Jason hole. And let's go ahead and figure this one out. So we have our LAV was 1.5 inches, and then we had 0.5 times 15, 16. Now gives us 1.03 inch. So our Rn comes out to be same equation, 1.2 LC T Fn, which is equal 1.2 times 103 times 38, and that was 65 KSI. So that gives us about 30.1 kip per bolt. Let's just keep an eye on this here. We gotta put the phi factor to it. So phi is equal to 0.75, and phi times Rn is equal to 0.75 times 30.1, and that will give us 22.6 kip per bolt. Now look at the bearing strength. This was the so this is a tear out strength. Now we're going to go ahead and look at the bearing. Let's change the color. And that's given from a same equation. Rn is equal 2.4 dt Fu. So that comes out to be 2.478, and 0.355 times 65. And that's equal 48.5 kip per bolt. We put the phi factor to it. It's Rn times phi times Rn is equal 0.75 times 48.5, 36.4 kip per bolt. That's this one. That's for bearing. So there's no edge bolt here in the beam web, so all bolts really are considered to be interior. So we got to look for the available. Let me make a different color so we distinguish it. Looking for tear out of beam web. So LC is equal S minus DH, and that's equal 3 minus 15/16, give us a 2.06 inch. And our Rn is equal 1.2 LC T FU. That's the same equation which we used, is a J3 6C, I think. Double check it. And so that comes out to be 1.2 times 2.06 times 0.355 times 65, and that gives us a 57 kip per bolt. Kind of high. Ain't this not gonna control? So Rn time phi time Rn, it comes out to be 0.75 times 57. That gives us 42.8 kip per bolt. Pretty good over there, so that's good. So now we're gonna say, okay, therefore, let me put this in a different color so we can all agree with. Pink is good, I like that. Therefore, tear out of the plate controls over bolt shear or bearing. And that was right here, 22.6. That controls, that's the lowest one we came up with. Okay, so the strength of the bolt group in the plate is computed by summing the strength of the individual fasteners. And phi time Rn become 1 bolt time 22.6 plus 2 bolt time 24.3 comes out to 71, which is bigger than our load. Let me explain this a little different way. Right here, change color, just show what I'm talking about. Make it green. Let's make it white. Okay, so this middle bolt right here, it came out to be this was came out to be 22.6, and the two outside bolts right here came out to be, the strength came out to be 24.3. So if you add all three of them up, and came out to be 71.2, and at the beginning we calculated 1.2 times reaction of shear reaction plus dead load and live load came out to 42. So this was due to the load, and therefore we okay right here. We got this one. Okay, next we're going to check the shear strength of the web plate and see if we're going to do that. So we came up here, we checked, do we see the bolt right here? It's good, that checked out. Now let's check the plate. We're gonna go to AISC J4.2A and you look at the available shear strength of the plate, and this given by this. We're gonna go through that. So the area, cross-sectional area, is equal LT, which is equal 9 inch times 3/8. And if you remember right here, our plate right here is 9 inches right there. And the thickness of the plate was 3/8, so the area, it comes out to be 3.38 inch square. And we're going to use equation J4-3, which is basically give us Rn is equal 0.6. This is the easiest stuff. We did this already. Fyt times Ag, and that's equal 0.6 times 50 times 3.38. So that gives us 101 kips. And if you put the phi to it, the phi is basically 1. And so phi times Rn is equal 101 kip, which is bigger than 42 kip. Okay, remember at the beginning we said, I wanted the thickness of, should we use a 1/2 inch plate or 3/8 plate, or then here you can find out if the thickness of the plate you did was okay. 3/8 is fine. We don't need to go for 1/2 inch. So this was a good check. Alright, so now we're going to go ahead and check the shear rupture strength of the plate. And if you look at the section J4.2, first we're going to find the area of subjected to a shear, net area of just net area for the shear. And that comes out to be L was 9 inches minus, then we had 3 bolts. So that's 3 bolts. And then we time 15/16 was the diameter we figured out before. Add 1/16 to it, and that makes it 1 inch. And then time the thickness, which was 3/8. Okay, so now A and V comes out to be 2.25 inch square. And Rn is equal 0.6 Fy, same equation, Fu, highlight. Fu time A and V, 0.6 times 65, 225. And that will give us 87.8. We're going to put the phi factor to it, so the phi is time Rn 0.75, 87.8. That gives us a 65.9, bigger than our 42, so we okay there. Okay, next we're going to go ahead and check the block shear rupture of the web plate. If we go to section J4.3, equation J45, which is, I wrote it down, we gonna go ahead and use table 9.3a. Let me write this down. Use table 9-3A, 9-3B, 9-3C. And the value we're going to use, N is 3, LH is equal to, LV is equal to 2.5, UBS is equal to 1 for uniform and 0.5 for non-uniform. You can read that section. But let's go to the table, see if I can get this camera here. So our LV was 1.5, and that's going to be for 7/8 bolt. It's going to be, no, our LV is 2, so we're going to be 73.1 right there, 73.1. Okay, so what we did, we're going to check block shear rupture using equation J45, 4.5, and we saw this equation, and we have the value already from that for that plate. N is equal to, we had 3 bolt, and our edge was 2 inches, our LV was 1.5 inches, and UBS, which was 1. Then using these 3 table, we calculated all those value. One came out to 73.1 for the tension, and for table 3B came out for the shear LD came out to 169, and the shear rupture table 9-3C came out to 146. We plug those back in this equation. We're going to find out it works out. 82.2 is less than 90. We're good. And therefore, our feet time RN is equal 82.2, which is more than 42. We're good there. Okay, next we're going to check the strength of the weld. I know we used the equation to figure it out, but we didn't say how we had like a 1/4 inch fillet. So let's check, see if the strength is enough. And that's given by this equation on page 810, 82A. And that equation basically is phi time Rn. Our D is equal 4, which is for 1/4 inch. If you go to that page, it will tell you what a D is, basically a weld shear in a 1/16 of an inch. And so phi time Rn comes out, we had 2 welds on both sides, 2 welds, and then multiply by 1.392 that the equation gave us, and time DL, which comes out to be 2 times 1.392 time D was 4, L was 9. And that phi time Rn comes out to be 100 kips, which is bigger than our 42 kips. We okay. So just let's recap all this. Let's go back, look at that plate at beginning when we're thinking designing this plate. Right here, this plate right there. This plate, when we were looking at it, this plate I'm talking about right there, and that plate, first we kind of sized it. We said, okay, we're going to use 3 holes, and then we sized it by 9-inch welding, and then from there we came up with the size. We said use 3/8, use it by 5/9, and then now we confirmed the size we picked. It was very good, actually. We could have gone even smaller. and worked out well. The bolt worked, the bolt string worked out, the rupture worked out, all that stuff worked out. And final step was if the weld is strong enough, and which it is, and that's what we figured out. So we're done with this plate. Next, we're going to go ahead and check this plate right here, this top plate. Check this plate out and see if we can do that. So we're halfway done. Go take a break. One thing I forgot to mention is, because it's passed by flange collars, a column flange rupture at the welds, and we can calculate the net area 14 inch. We can calculate Rn using this equation, and you can find out it's way, not even bother checking it, but they will check this one out too. Okay, we're gonna start with the flange. Let's take a look at the flange we have. This is the flange, and we're going to look at this flange plate right here. Another view of it was up here, right there, this same plate on top. And we got these bolt connections. We're going to do the same exact thing. Go through all those checks, make sure the plate that we selected, it passes. So we're going to come back. One of the first things we're going to do, we're going to calculate the flange force, and that's from chapter 11, equation 11.1, which is equal mu divided by the moment arm. Moment arm is the same as the depth of the beam in this case, which is 18. So we take the moment arm right here, and we're going to convert them to a kip inch divided by 18, and this will give us 168 kips. Okay, just like before, we're going to go ahead and continue the bolt shear strength. And from table 7.1, like before, we calculated the shear strength per bolt came out to 24.3 kips. And then we're going to look at the bearing strength. The bearing strength from the same area came out to be 76.5 kip per bolt. And the tear out strength, which is using these two equations right here we used before, comes out to be 90.8, and therefore I said the bolt shear controls in this case. The bolt shear controls over bearing and tear out. Alright, next we're going to continue with this. We're going to do the available tear out strength of the plate at the edge bolt. And using the same equation, we find the LC, which is 1.5 from the edge minus 0.5 times 15 over 16, and then calculate Rn using this equation right here. Comes out to 45 time phi factor, makes it 45.2. It's not going to control, still the other one controls right here. Still the this one control over there, which is the shear, bolt shear. So we keep going, checking the bearing strength of the flange per bolt, and using the same equation as we used before. Comes out to be 58.4 per bolt. And then we're going to check out the tear out strength of the flange at the interior bolt, and that comes out to be 68. So still, bolt shear controls over these two, and that was what? That was right here, 24.3. Next, we're going to check out the tear out of the flange edge bolt, and okay, just like before, so we're going to check out the tear out of the flange at the edge, and that came out to be right here, which does not control the bolt shear, which is 24.3 still controls. And then we do the group, and if we look at all of them, let me bring that picture up here. So all this 8 bolt right here, all 8 of them has the same, each bolt, the lowest shear capacity was 24, so we're going to multiply by 8, and that's where it come from. And we did all those calculations to figure out which one was controlling. That was a lot of calculation. So now we had at 24.3, there's 8 of them, comes out to 194, and that's bigger than 168. 168 is the flange force that we just calculated at the beginning right here. 168 is right here. This is the 168. So it's that kind of passes right there. So we're good there. And all right, so now we're going to go ahead and calculate the tensile strength of the flange plate. And they're using the same equation that we used before. That was a section, I think equation 11.1. This should be equation 11.1, and which is mu divided by dm. Now dm is, let me show you what dm is in here. We have the top plate right here, and there's a top plate right there and a bottom plate right there. So the distance between center of the top plate and the bottom plate is the dm. Basically it's d plus time 2 times half of the t. So, or d plus the, or that is d plus the thickness of the plate. And then we're going to calculate the PU. It comes out to become 161 kips. Then from there we're going to go to AISC, go to section J41A. We're going to calculate the available tensile strength. And first we're going to calculate the gross cross-sectional area, comes out to 525. And then we calculate Rn, which is Fy times Ag. This is a simple stuff, you already know this. And that become basically 263. And then now we're going to put the phi factor to it. The phi is 0.9 for that. Phi is equal 0.9. So phi times Rn is equal 0.9 times 263. And that comes out to become 237, which is the capacity. It's bigger than 161 kips, and we are, that's a kips, and we are okay right there. So we passed this one too. Okay, we're gonna go ahead and check the block shear rupture. To go ahead and check the block shear rupture of the plate. And of course, we're going to end up with the 3 different cases. Let's just look at this. The case 1 will be, let me make this a different color so I can explain it a little better. So case 1 will be if this will rip out like here to the end of the plate. From this right here, whoops, don't do that to me. Right here, if this rips out, so all this could rip out, and same thing on this side, go all the way to the end of the plate, come back here and rip out. So if this rip out in case 1, our L, this is right here is 1.5 inches, 1.5, and this distance also is 1.5. So my LEH is 1.5, my LEV is equal 1.5. And then we can go to the table later on, but let's go to case number 2. And this make this case 2. Case 2, if we have the inside breakout, like the block should be like this rip out be right here. All this will get ripped out. So that be case 2. And if that happened, then we have to go ahead and our LE, this is a 4 inch, the gauge is a 4 inch, and this is 1.5 inches. and this is 1.5 right there, 1/2. So here we got 4 inches, so it's basically 2 inches of the block, white block. So our LEH should become 2, and then LVE should be the same thing, and that's 1.5. If you look at between case 1 and case 2, case 1 is more critical than case 2 because LEH is smaller. So when this number is bigger, this is more critical. This is LEH is smaller. It rips out the other way, and this is rips out inside. So LEH makes 4 inches divided by 2 makes it 2 inches. And then we're gonna have case number 3. Let's write this down. Case 3 here. Case 3, what if we have like a rips out from here where the white line is going and come back to this 2 right here, and kind of goes out like this. That'd be case 2. Case 3 still got 4 inches, and this is 1.5 inches. Same drawing. So the shear failure will be through one row of bolt right here, which we went through this way, and then the 2 next to the column, and that's where it's going to be the failure. So now we're going to go ahead and calculate the block shear rupture in case 1. Again, go into this equation. We used this equation before, so we're going to use table 9.3a, 9.3b, and 9.3c, and equation J4.5. Our n and for the flange is 4. LEH in case 1 is equal LEV equal 1.5 inch, and our UBS, just like last time, is equal 0 as for uniform. So let me show you where we're gonna get that. Let's see if I can do that. Oh, that shows good right there. Okay, so there's a table right there, and I got LEV in 1.5 inches, and if you come back to 7/8, on the top you can see it says bolt diameter is a 7/8, and then we have a phi time FU time A and T divided by T comes out to 48.8. And so that came out to be, I'm going to just write all of them. Okay, we're going to go table 9.3b. So if you look at it, you look at the left, which would be right here. See if I can do this. Okay, right there, that's our, and there it's our LEVs in this line right there. And then you have n. N is equal 9, n is equal 6, our n is equal 4. And then we were looking for LEV 1.5, which is right there. If you go across, we're going to get with 4 is going to be 236. That's what we're going to pick. Hello. Okay, we're going to look at the last case, which is the table 9.3c. Our LEH is 1.5 inches, and our N is equal 4. So let's go look at that table, see if you can figure that out too. Okay, take a look at the table right there, and that's table 9.3, and the left column is the LEH, and we're gonna go all the way down to the bottom where n is equal 4. Let me see if I can hold this and do that. 4 right there, and we're gonna go to 1.5 inch, and then we're gonna go to where our bolt is 7/8. So across goes 7/8 is right there, and we should get a 205. And that right there, we're gonna write that down in there, and that's gonna become 205. Okay, so therefore we're gonna have our phi time Rn. It's gonna be 381 kip, which is way bigger than 161, and we passed this one with flying color. Okay, so we basically considering case 1 and case C. I think I have a typo here. Let me just fix this right here. This should not be case 3. Just take this out. So we're going to go ahead and use case 1 and case 3. Case 3, and because the numbers are bigger than what we have in a table, so we have to use the equation J4.3 manually rather go into the table. And this equation, you saw this equation before. Let me change color so I can do this. And then first we're going to found the area, gross cross section of the shear area. This is the shear area, and you can, if you've done this, if you take an advanced steel design, you know where this equation come from anyway. So that comes out to 788. And then we're going to calculate the net area for the shear, which is the average shear minus the taking out the holes, and comes out to be 526 right here. And finally calculating the net area, and that's basically gauge time the LEH minus 1.5 times DH plus 116 times the T, and that gives us 3. And for uniform is UBS is equal 1. Then Rn, plug in that equation, and we're going to end up with 400 minus 431. Therefore our Rn become 400, and put the phi factor to it, it comes out to 300, which is bigger than 160, so we check this one also. Okay, one more time. So beam flange block shear rupture, we have N is equal 4, LEH is equal 1 3/4, LV is equal 1/4. We're using same exact table 9.3 A, B, C. The reason this is a 3/4, let's take a look at this to explain that a little bit. Right here, for example, the distance from the center of the plate to the edge of the plate is 1.5 inches, which we knew that it was right there. But from the center of the hole to the edge of the beam itself is 1 3/4, because the plate is 7 inch, but the beam flange is 7.5 inch, and that's where that 1/4 comes in. And on the other side, we know this is 1.5 inches right here. So and BWLAV is 1.5 inches, but we got to take 1/4 away for beam underrun, because it can don't know how close that could be lined up with. So now we have that, then we're going to go through same thing, 9.3A, we go to the table, we find this, and 9.3B, we're going to find this, and 9.3C, we're going to find same thing like we done many times before on this problem. Then we calculate phi time Rn become 294, which is bigger than 168. We finally check this. Okay, the next one thing we're gonna do, check the fillet weld of the supporting column flange. That's the plate on top right here. Checking this weld right there, basically, against the column flange. And we did this at the beginning to size it, but now we're gonna double check it. So what we're gonna do, because this is perpendicular to the load, and so theta is equal 90. Then we have to go to ASCE J258, which is on page 16.1. Actually, I got them right here, and then we can use equation 8.2a to solve the length of the weld, and the length of the weld comes out into per 16th of the inch. So 51 divided by 16, the 3/8 will be bigger than that, so we can use 3/8 weld. Let's see if I can show you this for a second. So there's the that section. Look at the one that says D, weld size in 16th and of inch. And if I go to previous page, actually then here they show, they might show that equation J2. They did it one time, but anyway, the equation for KDS is also in here. So our fillet welds going to come back to 3/8 of an inch. We're going to use that. Okay, next we're going to go ahead and check the compression flange plate and the connection. We're going to go to section J4.4, and K is equal 0.65 for a fixed end. You've seen this from column design. And L is equal 3, which is the distance between the bolts, and the radius gyration, we're going to calculate that. Moment inertia, which is equal, basically the plate is 112 BH cubed, so it'll be 112 BB7H is a 3/4 inch divided by 12. Then we get divided by area, and we get this number. And then KL over R ratio comes out very small, 8.99, which is less than 25. Then basically we're going to say, okay, Pn is equal Fy times Ag, and it comes out to this number, which is bigger than the phi. Put the phi factor to it, it comes out bigger than 161, and we good. All right, we're going to go next. Okay, next we're going to go ahead and check the local buckling of the flange local buckling of the column. If we go to section J10.1, let me bring that up, see if I can show you again. And right there, can you see that? That's better. We're going to look at this section, flange local buckling, and that's on page 16.1.150. So from there, we're going to go ahead calculate the so the available strength is going to be, we're going to use 0.15 times BF. That gives us a 2.19. This is the distance we're looking for, but the length of the loading in the plate is about 7 inches. So this number is less than 7 inch. That should be less than 7 inch, and there, because of that, we should really check the flange local buckling. And if you look at this number, below this number, we don't worry about the buckling issue. But if the number is bigger than here, you check for local buckling. And in here, our plate is about 7 inch. And it makes it, we should check the local buckling. Then, for do that, we're going to assume the concentrated force as applied to the column at a distance greater than 10 times F, which would be 10 times 0.78, which comes out to 7.8 inches. And then we go back to that equation. We plug in that equation we just showed you, 6.25 times Fy flange times Tf flange squared. And when I do that, I get 190. And when you plug the phi factor into it, become 171, which is bigger than our load of 160 we checked out. Next, with the same page I showed you a second ago, we're going to go ahead and look at the web local buckling of the column. Okay, finally we're going to go ahead and check web local buckling and web crippling. So we're going to assume that the concentrated force is applied at the distance of at the end of a column greater than the depth of the column itself, and then we're going to go use table 9.4 and equation 961. Let me bring you back here. So here we're going to use local web local yielding, and then we're going to go do a web local crippling, and then we're going to go to table 9.4. Let me bring that table up right here. Okay, so you're going to go ahead and find W14 by 99, which is up right there, and then we're going to go ahead and write down phi R1, phi R2, phi R3, and phi R4. And these are the numbers right there. You can look at the table yourself. And then, let me see. So once I did that, we can go ahead and figure out from the table, we get phi R1 83.7, phi R2 become 24.3. And this is the equation we just saw. We plug in an equation, and then we find phi time Rn comes out to 186, which is bigger than our 161 we checked out there. Then we do the same thing with web local crippling. You're going to use equation 964a and calculate it from the table. We get phi time R3 and phi time R4, and then we plug it in. Our phi Rn become 233, which is bigger than 161, and we checked. And this is the end of it. If you have watched this video all the way to this end, I'm going to give you a thumbs up. And this was a really hard problem and included a lot of computation, but that's how you design a beam to column moment. You got to check for everything, and then when you do all this check, then you can sleep comfortably, sleep, and then it's okay, the design is complete. I hope this was useful. You have a wonderful time. Take care.